Welcome back to ECE 442-542. What I want to do now is continue through lecture 5.2, and this particular segment is dealing with the first performance specification, which is the settling time specification. And how do you translate this settling time specification into second order Z-plane pole locations? Remember, we have our different breakfast cereal shapes. We have circles for settling time. For percent overshoot, damping ratio corresponds to these logarithmic spirals or hearts, and the peak time corresponds to these wedges or angles. For settling time, we have these concentric circles depending on how big our radius is, and the larger the radius, really the slower the system. So suppose somebody gives you a settling time and they want to know, okay, where do I put my poles? That's what we mean by a performance specification or a design specification. Somebody gives you a settling time. Let's say they give it to you in terms of number of sample periods, or they could give it to you in actual units of time if you know the sample period. So if they give you T settle as, let's say, 4 seconds, and they give you a sample period, then you can back out the number of sample periods n sub s. So n sub s, in that particular case, solving this equation for n sub s says that that's just T settle in absolute units of time divided by the sample period in seconds per sample. That's now n sub s. Well, if we know n sub s, the number of samples to get us to within 1% of where we started, we can use this familiar expression, x, the value of x at time n sub s, and again we're looking at this single time constant system where r is our time constant. We're trying to find what's the radius r, the distance away from the origin in the z-plane, r raised to that number of samples times the initial condition needs to equal 1% of where you started, and that's where this 1% settling time comes from. The initial value really cancels itself out, so it doesn't really matter what that is, and we can now solve this for r n sub s is equal to 0.01. That can now be solved for r by first taking the log base 10 of both sides, and the reason we're using log base 10 is because log base 10 of 10 to the minus 2, or log base 10 of 0.01, is a nice number. It's actually minus 2. Now we know that n sub s, the number of samples, times log base 10 of r is equal to minus 2, and we can solve that for log base 10 of r. And I'm going to call that an important equation, so I'm going to give it a star. Log base 10 of r is minus 2 over n sub s. N sub s is the number of sample periods to take us to 1% of where we started. If we solve that for r, then now we know that, or we take the antilog of both sides, we now know r is equal to 10 raised to the exponent minus 2 over n sub s. If that's the case, what can we say about the relationship between the number of samples, what is its size, is it small or is it large, and what does that correspond to relative to the radius? And this may get a little bit confusing because it's what? It's raising 10 to a negative power, but we could also view that as r is equal to 1 over 10 raised to the 2 over n sub s. Maybe that makes it a little easier, maybe not, because n sub s is now in the denominator of an exponent. But let's say that n sub s is small. If n sub s is small, then the exponent is going to be, if n sub s is small, then relative to a larger, or maybe we look at a big n sub s first. So let's let n sub s be really big. So it takes us a long number of sample periods, a large value of sample periods to settle. If n sub s is large, then 10 is being raised to a very small exponent. Well, if that's the case, we now have 10 raised to some power, but that power is positive. So it's a little bit bigger than 1, but 1 over that is actually going to give us a large value for r. Now, if n sub s is small, if n sub s is smaller than that, then r is also going to be small. Maybe I should say larger and smaller, because these are all relative, and it's maybe even easier to think about if you just think about what's going on here relative to large and small. If r is large, which corresponds now to this radius, then that's closer. Let's say if everything is inside the unit circle, that r value is closer to the unit circle, so it's going to correspond to a slower system, which means that r is larger. If we were interested in a smaller radius, then that's going to exponentially damp out much more quickly, and consequently, with a small r, n, the number of sample periods to get us within 1% of where we're going is also going to be small. Let's look at one case. Suppose the number of samples before we go from where we started to 1% of where we started, let's say n sub s is 60 samples. That's 10 to the minus 2 over 60, or that's now 1 over 10 to the 1 over 30th. Again, that's not a number much bigger than 1, but it is a little bit bigger than 1, and that gives us an r value of 0.926. What that number of samples corresponds to obviously is dependent on the sample period t. If we're sampling at 100 milliseconds or 0.1 seconds, then it would take us 6 seconds to get to 1% of where we started. Or if the sample period actually corresponded to 10 milliseconds, then it would only take us a little bit more than half a second, or 600 milliseconds, or 0.6 seconds to get to 1% of where we started. Even for the pole being at exactly the same place, the pole is at 0.926. What that corresponds to depends obviously on the sample period capital T and how fast or slow your corresponding system is. Suppose now somebody gives you an R and they say, oh, what's the 1% settling time? Well, now we can go back and we can use this star, and we're given now R. Let's solve for n. So now we know star, which is log base 10 of r, is equal to minus 2 over n sub s. We can multiply both sides by n sub s, divide both sides by log base 10 of r. We're given r. Everything on the right is known. Now, since we want n sub s to actually be an integer, we'll basically take the smallest integer greater than or equal to what that numerical value is inside the ceiling function. Suppose r is 0.8. How many samples does that correspond to in terms of a 1% settling time? N sub s, capital N sub s, is now minus 2 over, this is just applying that formula, log base 10 of 0.8. Log base 10 of 0.8, it's a little less than 1, so we have a negative number. That's minus 0.09691 in the denominator. Dividing that into 2, or minus 2, gives us 20.6. We find the smallest integer larger or greater than 20.6. So an R value of 0.8 corresponds to 21 sample periods. Hopefully that now helps you better understand this relationship between settling time, that specification, and the distance your two dominant poles are going to be away from the origin in the z-plane. How big is the radius of the circle? If we have a settling time, we know r needs to be inside the unit circle. What that particular value of r is or equals obviously depends on our settling time. And the settling time numerically is going to depend on what our sample period is in terms of the settling time absolute time versus the settling time in number of sample periods.